In this video, we're going to start the process of constructing real numbers in a place that might seem kind of unusual. We're going to look at sequences of real numbers. So first we're going to define what sequences are. We're going to look at some examples and find different ways of expressing sequences. We're going to define what it means for a sequence to converge. And then we're going to do an example of determining what a sequence converges to and actually proving it. Now, back in your calculus days, when you saw a sequence, you probably saw it as an ordered list of real numbers. And that's how we're going to write sequences here. But I do want to let you know that that's just a model of how we think about sequences. There's a formal definition that we'll get to in a little bit. But right now, ordered list of real numbers, just fine. So here are some examples. If you have a sub n equals 1 over n, note that when we write this in this sort of bracketed form with the formula, and we have the n equals 1, that just tells us where our n starts, and then the infinity indicates that you keep on going forever. You don't have to start at n equals 1, but most of our sequences are going to start at n equals 1. That's just where I like to start. What can I say? So that is going to give us 1, 1/2, 1/3, 1/4, 1/5, etc. For a sub n equals n squared, that gives us the sequence 1, 4, 9, 16, 25, etc. N factorial, we get 1, 2, 6, 24, 120, 720, etc. And one of the things you may have noticed about all those sequences, at least those examples, is they all depended on a formula, which seems just like a function. And in fact, if we rewrote those sequences as f of n equals 1 over n, f of n equals n squared, f of n equals n factorial, we see that it actually is a function. And the only thing we really demanded of our function is that our inputs had to be natural numbers. In other words, we could think of a sequence as a function whose domain is the natural numbers. And that gives us our formal definition. The sequence is a function f from the natural numbers to the real numbers. And if that f from the natural numbers to the real numbers looks a little familiar, that was what we were talking about when we were looking at the proving the real numbers were uncountable, right? We were looking at a function from the natural numbers and real numbers and proving that that wasn't onto, but we were also kind of looking at sequences there. So sequences was even in that uncountable proof that we had. Now I should notice there's a connection between this function and the ordered list that we were looking at, f of n equals an, and I will almost certainly never write a sequence as a function ever again. So, but I just wanted to write that down because it is the formal definition. So just like any other function whose inputs are real numbers, it's not all the real numbers, just the natural numbers, but natural numbers are real numbers, and whose outputs are real numbers, we can talk about our sequences being bounded above. That means there is some real number that is bigger than or equal to all the terms in the sequence. We can talk about bounded below. That means there is a real number that is less than or equal to all the terms in the sequence. We can talk about bounded, which just means it's bounded above and bounded below. We can talk about increasing, which means if m is less than n, then a sub m is less than or equal to a sub n. And if it's strictly increasing, it's a sub m is less than a sub n. If it's decreasing, we get if m is less than n, then a sub m is greater than or equal to a sub n. And if it's strictly decreasing, it's a sub m greater than a sub n. Monotone just means it's either increasing or decreasing. We love increasing sequences. We love decreasing sequences. Monotone sort of puts those two concepts together. Now, back in Calculus 2, you might remember that we would talk a lot about when sequences converge and when they diverge. And we're going to do that. We're going to talk about that here. It's going to be our focus about sequences. And if you remember our language around that, convergence just means the sequence has a limit. And so if we came across the sequence 1 over n, we use a lot of our intuition, right? By saying, okay, 1 is in the numerator, the denominator gets huge, that means it's getting close to 0, so 1 over n converges to 0. And there's nothing wrong with intuition, But now that we're in an upper level math course, of course, we want to have a way of actually proving those things. So we're going to ask some very fundamental questions that we wouldn't have bothered with in calculus because they were sort of, I don't know, we say they're obvious or intuitively obvious, but they're important to prove, like what does convergence even mean in a precise way? Specifically, what does it mean for the sequence an to converge to some real number L? All right, well, what we're going to do is actually kind of similar to what we've done throughout this course. Start with our intuitive notions of what this means, and then work our way toward a precise definition. So in the old days, we'd say as n, quote, goes to infinity, a sub n, quote, goes to L. So goes to infinity and goes to L is doing a lot of heavy lifting there. So what we're going to have to do is kind of unpack what those mean and see if we can put it in a precise definition. Well, it goes to infinity. We're not really going to infinity. Infinity isn't a destination. It isn't a number that you're actually going to get to. All it really means is n is getting really large without bound. So what we're really saying is as n gets really large, whatever the heck that means, a sub n gets close to L, right? Goes to L, goes to an actual number. That means you're getting close to L. You never actually get there, maybe, or maybe you do, but you get close within a certain distance of it. We're talking about distance between those two numbers. So we're going to have to make precise two similar but different ideas. What does it mean for a natural number n to be really large? What does it mean for the real number a sub n to be close to the real number L? All right, so we've made some progress though. As n gets really large, a sub n gets close to L. Well, n gets really large, what that really means is that I'm going to choose a number that is sort of the standard for being really large. And n being really large means you're bigger than that number. Now, that number may be different for different people, so we have to be a little bit flexible about what that number means. So we're just going to call it n, right, or big N. So if n is larger than something that we believe is a really large number, we'll just call it n. The absolute value of a sub m minus L is always smaller than some really small number, right? So we want it to be really close. That means less than a small number. And again, we don't agree maybe on what that small number is. So for now, we'll just call it epsilon. And just, whatever your small number is, you'll put that in for epsilon. Whatever my small number is, I'll put it for epsilon. We want to be very flexible about what we want that standard to be. And so kind of rewording this, whenever someone presents to us their standard of epsilon of what it means for a sub n and L to be close, we can meet that standard by presenting our standard for n being large. So anytime someone else gives us an epsilon saying you have to get the distance less than epsilon, I scurry around, I find a big N, I say, okay, as long as your little n is bigger than this big N, then that'll meet your standard. Making it more precise still, for every epsilon greater than 0, for every standard of being close, we can make the absolute value of a sub n minus L less than epsilon simply by making little n bigger than big N for some natural number big N. And that finally brings us to the definition of convergence. We say a sequence a sub n converges to the number L if, for all epsilon greater than 0, there exists some natural number big N, such that if little n is bigger than big N, then the absolute value of a sub little n minus L is less than epsilon. So that's a real mouthful, but sometimes it really helps to think of it as sort of a push and pull between somebody gives you a standard of what it means for the numbers to be close, you give them a natural number that is big enough to satisfy that standard. And I don't know, might be helpful to think of you as like a competition between you and Peeves. I don't think we've talked about Peeves yet. Peeves is that person who is very much devoted to logic, but is also devoted to making your life as difficult as possible. So in this situation, Peeves is going to give you a teeny tiny number epsilon that they think that there's no way you can get within that epsilon, and then your task is to find that big N that actually does get less than that epsilon. So Peeves gives you an epsilon, and then you respond with a big N to satisfy Peeves' standards. And you need to be ready for any epsilon that Peeves gives you. That means you must plan ahead, have a big N handy for every possible epsilon greater than 0 that Peeves can give you. All right, so if you actually have a sequence, AN, and want to prove what it converges to, how do we solve this problem? Well, if you think carefully about it, there's actually two problems, right? One problem is, what the heck is even the limit going to be? If you look back at that definition, it doesn't tell you how to find the limit. It only tells you, right? It only tells you how to check if the limit works. We have to actually guess the limit. And actually, one of the nice things about guessing is you never have to justify to me what your guess is. You could have logically come to it through some very methodical way, or you could have just woken up from a fever dream and says, "Oh, the limit is 5." You know, that's fine. I don't care what it is. As you can guess whatever you want, as long as you can verify that it works, everything's okay. Now, once we have found our L, or at least given a guess, our priority is to find out what we have to make happen in order for the absolute value of a sub n minus L to be less than epsilon. Our focus is going to be on, we need to meet Peeves' standard, his epsilon. And then we use that to figure out what our big N is going to be. So focus on the challenge Peeves is giving you, find the big N that meets that challenge. So we can have different values of N for different values of epsilon. That's normal, right? If you had a big epsilon, you could probably satisfy that with a relatively small big N. But if Peeves gives you a teeny tiny epsilon, you may need a huge big N to do that. So it's okay to have different values of big N for different values of epsilon, but you can't have different values of N for different values of little n, right? You can ask Peeves, what is the epsilon that you want to give me, and then I'll give you the big N. But you can't ask Peeves, give me the epsilon, but can you actually tell me what the little n is as well? Because I need to do that. I need that to figure out my big N. That should not come into your consideration. And then finally, after we have our N figured out, which is usually done in a very non-linear way, we need to rewrite our proof so that it logically goes in a linear fashion. Make sure it's in the proper form. All right, so remember our old pal 1 over n. We're gonna go ahead and prove that one converges to, what did it converges to again? Let me see. Well, by whatever intuition or whatever other method that you use, we believe that it converges to 0, right? So we want to prove that 1 over n converges to 0. And we're going to use the definition to prove it. All right, so suppose epsilon is greater than 0. That's the standard that Peeves is giving you. Question is, what does it take for absolute value of 1 over n minus 0 to be less than epsilon? Well, let's see. 1 over n minus 0. So that's the inequality that we're working on. 1 over n minus 0 is just 1 over n. And the absolute value of that, n is a natural number, which is positive. So that's just going to be 1 over n. So we get 1 over n is less than epsilon. And then it seems like a good idea to maybe solve for n. So if we multiplied both sides of that inequality by n and then divided both sides of that inequality by epsilon, those are both positive numbers, so we don't have to worry about flipping the inequality. And then we flip that around, we get n is greater than 1 over epsilon. So that's actually kind of nice. It tells us that as long as little n is greater than 1 over epsilon, that will meet Peeves' standards. And it's different for every epsilon, but that's okay. So we only need our big N to be an integer such that big N is greater than epsilon, and then the rest of the argument should work out. All right, so that's kind of our scratch work to figure out our big N based upon our epsilon. Now we're going to go ahead and actually prove the theorem, starting from our assumptions and working toward our conclusions. All right, so remember, to prove that 1 over n converges to 0, we assume that epsilon is greater than 0. We don't assume anything about epsilon except that it's greater than 0. And then we're going to show that we can find big N in the natural numbers such that for all little n bigger than big N, we have the absolute value of 1 over n minus 0 less than epsilon. So we're going to choose any integer big N such that big N is greater than 1 over epsilon. And we should make a little note that such an N will exist no matter what epsilon is, since the integers are not bounded above. So 1 over even if epsilon's tiny and 1 over epsilon's massive, no matter how big it is, it can't get so big that there isn't a natural number that's bigger than 1 over epsilon. So then we need to prove that for all little n in the natural numbers and little n bigger than big N, we have the absolute value of 1 over n minus 0 less than epsilon. Well, let's see. So we've done this part of it before. The absolute value of 1 over n minus 0 is equal to 1 over n. Since big N is greater than 1 over epsilon, it follows if we multiply both sides by epsilon and divide both sides by n, we get 1 over n is less than epsilon. Furthermore, little n is bigger than big N, so if we divide by little n and divide by big N, we get that 1 over little n is less than 1 over big N. And then we're going to go ahead and put these together. We get the absolute value of 1 over n minus 0. That's 1 over n, which is less than 1 over big N. And 1 over big N is, if we look a couple lines up, is less than epsilon. So that tells us that the absolute value of 1 over n minus 0 is less than epsilon. That means 1 over n converges to 0. And that's the end of the proof. All right, so I think you're ready to go ahead and work on the activities for Introduction to Sequences. Just go ahead and click the link below this video.